Welcome back to our course, Fundamentals of Operating Systems, based on the text Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Cagney, and Peter Galvin, published by Wiley Publishing. In the last lesson, we began our discussion of several of the CPU scheduling algorithms in use today. We began with the simplest of them all, first come, first serve. Now we're going to move on to the next one in our list, shortest job first. So let's begin. Another scheduling technique is shortest job first. This algorithm associates each process with the length of its next CPU burst. When the CPU is available, it's assigned to the process that has the smallest next CPU burst. If the next CPU burst of two processes are the same, then first come, first serve scheduling is used to break the tie. Even though this approach is called shortest job first, it doesn't really consider anything but the length of this job's CPU demand. It doesn't consider input-output requests. As an example of shortest job first scheduling, consider this set of processes with the length of the CPU burst given in milliseconds. Using shortest job first scheduling, we would schedule these processes according to this Gantt chart. The waiting time is 3 milliseconds for process 1, 16 milliseconds for process 2, 9 milliseconds for process 3, and 0 milliseconds for process 4. So the average waiting time is 3 plus 16 plus 9 divided by 4, or 7 milliseconds. By comparison, if we were using first come, first serve scheduling scheme, the average waiting time would be 10.25 milliseconds. Moving a short process before a long one decreases the waiting time of the short process more than it increases the waiting time for the long process. Consequently, the average waiting time decreases. Although the shortest job first algorithm is optimal, there is no way to know the length of the next CPU burst, so it really can't be implemented at the CPU scheduling level. One approach to this problem is to try to approximate shortest job first scheduling. We may not know the length of the next CPU burst, but we may be able to predict its value. We expect the next CPU burst will be similar in length to the last one. By computing an approximation of the length of the next CPU burst, we can pick the process with the shortest predicted CPU burst. The shortest job first algorithm can either be preemptive or non-preemptive. The choice arises when a new process arrives at the ready queue with a previous process still executing. The next CPU burst of the newly arrived process may be shorter than what is left of the currently executing process. A preemptive shortest job first algorithm will preempt the currently executing process, whereas a non-preemptive shortest job first algorithm will allow the current process to continue its CPU burst. Preemptive shortest job first is sometimes called shortest remaining time first scheduling. As an example, consider these four processes with the length of the CPU burst given in milliseconds. If the processes arrive at the ready queue at the time shown and need the indicated burst times, then the resulting shortest job first schedule is depicted in the Gantt chart. Process 1 is started at time 0, since it's the only process in the queue. Process 2 arrives at time 1. The remaining time for process 1, 7 milliseconds, is larger than the remaining time by process 2, 4 milliseconds. So process 1 is preempted and process 2 is scheduled. The average waiting time for this example would be 6.5 milliseconds. Non-preemptive shortest job first scheduling would result in an average waiting time of 7.75 milliseconds. Can you think of a possible problem with both non-preemptive and preemptive versions of this approach? What if there's a job with a very long CPU burst, such that whenever one of the shorter jobs is finished and terminated, a new short CPU burst job may be added to the queue? Wouldn't the new short job be placed ahead of that long one? Doesn't that present the possibility that the long CPU burst job will starve? Although I said we were going to discuss one scheduling algorithm, shortest job first, in fact what we discussed were two scheduling algorithms, shortest job first and shortest remaining time first, although the authors chose to call them both shortest job first, with one of them being preemptive and the other being non-preemptive. One scheduling algorithm or two is not particularly important, just as we understand that there is a difference between the preemptive version and a non-preemptive version. And another thing to consider too, when we were discussing the time savings for shortest remaining time over shortest job first, we didn't take into consideration the fact that a context switch takes time. Now that wasn't measured. So which is the quicker? Shortest job first, which has no context switches because it's non-preemptive, the job would finish completely and give itself up, or shortest remaining time, which would have a context switch every time a job was interrupted when a shorter job came into the queue. You understand the difficulty for developers in determining what approach to use when it comes to CPU scheduling, because there are so many variables that one must consider. There are trade-offs that one must consider. Well, that concludes that lesson. We'll take a break right here. Take a look at your notes. Take care of any business that you need to take care of. When you are ready, come on back and we'll move to the next example of a CPU scheduling algorithm.